Hi guys, welcome to my video. This video is on geometric dimensioning and tolerancing, GD&T. Right, some of the contents that we're going to go through, what GD&T is and why do we need it, the sort of people that should be watching these videos, the information that I've used to put these videos together, what standards do most companies use, what do we need, and the main differences between the standards. Different types of dimensions used, and a bit of a GD&T knowledge test. That's what we're going to cover in this first video. This first video is really important to understand some of the standards that drawings are done in accordance with, and how you read and how you do drawings changes massively depending on what standard you use. So this video is going to be quite important for a lot of people to understand properly. Okay, geometric dimension and tolerancing is a system for defining and communicating engineering tolerances. It uses symbolic language on engineering drawings and on 3D models to describe what you want, basically. So instead of saying this face needs to be flat, or this face needs to be square, or this face needs to be parallel to this face, so we get rid of all them words and whatever that would be on the drawing normally, and we replace them with these boxes. So these are the symbols, the GD&T symbols that we use. The first bit basically tells us what sort of symbol we want, or what we're trying to define, the position of something. This gives us the tolerance band. In this case it's a diameter of 0.15, and this gives us what it's relative to. So the positional tolerance is a diameter zone or a cylinder zone, and it's relative to datums A and B. So these are the sort of symbols that we're going to use for GD&T. And we're going to go through how we define in the drawings the symbols, where they need to go, the application of the symbols, and later on in some of the later videos I'm going to put lots of examples of how to use these symbols properly. Right, so it's used to minimize the stack up of components and dimensions. It can help with working out if components will fit together very quickly. It allows far greater control over form, orientation and position of features as compared to standard dimensions. I think one of the most important things here is you can minimize the words. So when you're dealing with different countries, for example, they'll understand the same symbols. It's very difficult to get the symbols wrong. They mean the same things even in different languages. That's one of the good things about GD&T. And we can actually reduce the manufacturing cost using this method. And we'll go into some of that in a bit. And one of the reasons why is because we can increase the available tolerance on certain features while using this system. So the thing is here, I've put a comment at the bottom. If you think about just drawing box dimensions all at the same time, and the tolerance is basically what's in these boxes. This is sort of how the system works. So we define the position of something using box dimensions. And box dimensions don't have a tolerance on. So if you think of it as just drawing that dimension or that feature using the box dimension in a CAD package or whatever, so you're drawing it exact. And then the tolerance that applies is just what's in these boxes. And that's sort of how the GD&T works. So who should be watching these videos? I'll just put a quick list. So anyone that's got anything to do with engineering, where you need to read or create engineering drawings. Anyone that's got anything to do with manufacture of engineering parts. So some of the people that need to understand how this system works are design engineers, draftsperson, manufacturers, so shop floor personnel. I think there's some gaps in knowledge of people in manufacturing of exactly reading engineering drawings and understanding the tolerancing on particular components. And this is incredibly important because if you come into jig bore some holes in a component and you don't know how accurate the roundness or the cylindricity is, or you don't know how good the position is, etc., you don't know necessarily what manufacturing methods to use to produce them features as quickly and to the right standards and to the right accuracy. So you do need to understand the tolerances involved before doing a job, not after. So I've put there production engineers, so people writing the actual programs for the machines, people doing the planning for the jobs that go around the shop floor, assembly engineers, inspectors, lots of people need to understand how engineering drawings work to make sure that parts fit together properly, parts get inspected properly, we know where they're not to drawing, we know how to alter components to put them right and things like this. Okay, so the information I've used to put these videos together, various British and American standards. There's two main standards that we tend to use with GD&T, and I'm going to go through some of them in a bit. My previous experience working in manufacturing and in design and drafting, actually seeing some of the problems with parts not fitting together. I've got some information from the internet, and I've used NX11 to draw a couple of examples. So which standards do we use? What are the main differences between some of the standards? So years ago we used to use in this country BS 308, which I've got at the top there. So there's 3 parts to BS 308, and that's generally now, most people are now working to BS 8888 instead. Now there's some differences between the standard that you need to understand with regards to GD&T. And the other, so you've got sort of the BS and ISO standards, and then you've got the ASME standards, the American standards, and I've just put what ASME stands for at the bottom there. So the British Standard 308 basically gives you a lot of the GD&T inside it, and the BS 8888 points you into different directions of different standards to look at basically. There are some differences between the standards, and we're going to go into that in a minute, and it's quite important to understand that. Okay, so differences between the BS and ISO standards and the ASME standards. This is one of the most important things in reading engineering drawings or doing engineering drawings. You need to understand what system's been used in creating them drawings. So even if a company is using their own standards, generally they'll be based on one of these two standards. So it's either the BS and ISO standards or the ASME standard. It's one or the other generally. Now years ago, in the BS 8888, the earlier versions, you used to have a symbol with an I in it or a symbol with a D in it to define what system had been used in creating that engineering drawing in the first place. So basically the British standard nowadays uses the triangle with the I in it. So that is the system of independency, and you've got the triangle with a D in it, the system of dependency. Now the ASME system works on the system of dependency, and the ISO standards at the minute work on the system of independency. Now the differences between these two standards are very, very important to understand. So basically what it's trying to tell you is how you measure components is different basically. The system of independency means you treat the form of a component or the form of a feature and the size of a feature independently. So we've got a cylinder, a hole for example. We treat the size of the hole as one thing and the roundness or the cylindricity of that as something different. So there's two different independent things that get inspected independently. Now the triangle with a D in it, the system of dependency, is basically using an envelope rule. So it's an envelope of perfect form at maximum material. So what does that really mean? So what it means is that hole, when you've got the most material in there, has to have perfect form. It has to be perfectly round, and it has to have perfect cylindricity. So roundness over its length. So basically when you're doing a drawing with a D in it, you don't need to put a lot of roundness or cylindricity symbols and things on the drawing, because the size itself, the tolerance on the size and tolerance define how round something can be, or the cylindricity or the straightness and things like this. Now my personal preference here Obviously the ASME uses the triangle with a D in it, so you don't see a lot of ASME drawings with roundness and cylindricity and things on it because you don't need it, generally. My preference is, where I work, we make a lot of one-off components. And the problem with this is that the manufacturers, I don't think, really understand the main differences between these two systems. So my preference really is to use the triangle with the eye in it, the system of independency. And the reason for that is if you need something to be round, you need to put a roundness symbol. If you need it to be have good cylindricity, you put a cylindricity symbol. So the manufacturers don't miss it. The problem with using the triangle with a D in it is it's a lot easier from a design point of view, a drafting point of view, using the ASME system or the British standard with the triangle with a D in it, which is the same thing. Because you've not got to put cylindricity, roundness and things like this. So it's not an issue for the design side of it. The problem is if it doesn't actually get inspected correctly. So if you're doing a production run, using the ASME is a good system, or the triangle with a D in it. If you're doing one-offs, I find it's better and safer to put the form tolerances that you require on the drawing itself, rather than using the envelope rule. And we're going to go into the envelope rule in a little bit. So basically it's so important, it's actually rule number 1 of the ASME standard. So I've just put there the ASME 14.5. It's basically what I've just said. There's an envelope of perfect form corresponding to the maximum material size of the feature is defined as rule number 1. So it's actually rule number 1 of ASME, and it's that rule that I don't think a lot of people really understand. And it's one of the most important things, which is why it's rule number 1. It's basically how you inspect a component, how you measure that part. With the CMM nowadays, people tend to take an average size a lot, I find. So you've got a tolerance on a diameter, and someone will take an average size of something and they'll report that average size is within the tolerance. Now that's not really what you want. You need to make sure they understand that rule number 1, that envelope rule of perfect form. Otherwise components may not fit together properly because they've got bad form. And basically in ISO 8015 that actually tells you about the system of independency, the fact that the size and form needs to be treated independently, and it tells you how to measure the components. Right, so this is the ISO 8015, and just basically tells you what I've just said. Basically there's no relationship between the size and the form, they're treated independently. So this is actually used now more instead of the triangle with the eye in it. So basically you say it's drawn in accordance with BS 8888 and toleranced in accordance with ISO 8015. So that does the system of independency. So it must be clear when you're doing a drawing which system you're using or which system your company standards are based on. It has to be based on one or the other really, for people to understand, what you're actually trying to do. Okay, so different types of dimensions. So at the top we've got the box dimension, and this goes with the GD&T. So it's a box dimension or a basic dimension, a theoretically exact dimension. So some of these things it's called in different standards or in different places, but it means the same thing. So it's got no tolerance, it's drawn exactly. It's used to locate a tolerant zone. Right, so there's some differences between the ASME and the BS. The ASME, you can actually use box dimensions as gauge dimensions, and you can use them on chamfers and various other places. But using the British standard, you can only use a box dimension where you're using a tolerance control frame. And a tolerance control frame is basically what this is. This is a tolerance control frame, which is controlling what the tolerance actually is on the feature that you're trying to define. Okay, so then the next one down, we've got a reference dimension. So in brackets means a reference dimension. So it's not used as an inspection dimension. It's not required to manufacture the component. So if you've got a stack up of dimensions and it's the stack up of dimensions that's important, but the overall length of the part may be a particular dimension. So the overall length may be just a reference, for example, and it may be the distance between features that you're actually controlling. But you might look at it and go, how long is that? Is it a meter long? Is it 2 meters long? Whatever. So it's just to give you a reference. Yeah, it's roughly this. It's a reference. Or you can define the 36,26 could be defined elsewhere as a box dimension, for example, and then later on you might want to call it as a reference. Okay, the next one down is a normal dimension, usually subject to the general drawing tolerance. So that's sort of the normal dimension you see most of the time on drawings. And then the next one down, you don't see this nowadays really so much because we use CAD, everything's usually to scale. But you see it sometimes on proper drawn drawings, as it were, that are done on drawing borders. So underlined dimension just means it's not to scale. So you might see it now and again, but not very often nowadays. Okay, so this is to do with a quick knowledge test, just to see if you understand what some of these symbols mean. Generally speaking, some symbols, the way I tend to look at this is some symbols are really for a 2D feature, and some symbols are for like a 3D feature. So understanding that to start with is quite important, and understanding which symbols control form and which symbols don't. So some symbols can control form, some symbols orientation, some symbols position, and some symbols can do all three or a variation. So it's understanding how we can use these symbols. So if you want to pause the video here and have a go at this and just tell me what these symbols are and which ones control form and whether they control a 2D or 3D feature. Okay, so I'm going to move on now and show you the answers. Okay, so the top one is roundness or circularity. So it's called different things in different standards, but it's the same thing. It is a form tolerance, which is why I've just highlighted it in green. So it's controlling the roundness or circularity of a part. So this is actually a 2D feature. So we control the roundness at any section through the part. But it's not controlling the straightness of the part, if that makes sense. It's only controlling the roundness at that particular section. So it's a 2D feature. Okay, so the next one, profile tolerance of a surface. So this is a 3D feature. It's controlling the profile tolerance of something relative to datums A and B in this case. So this is basically controlling the position of something. It's controlling probably the shape of something. So it's doing quite a lot for you, and it's doing it over a 3D surface. The next one is total runout. So total runout is slightly different to single runout. If we look further down, we've got single runout and we've got total runout. So total runout, basically what you're doing is you're controlling, you can do runout on a face or you can do it on a diameter. So on a diameter, it's controlling the roundness. But in this case, total runout, you basically put the DTI on the diameter and you guide the DTI along the surface at that setting. So total runout can actually do squareness for you. It can do cylindricity for you. So it's a 3D feature or tolerance. On a face, it can actually do flatness. It can tell you if the face is dished in one direction or another direction. So total runout is doing a lot of things for you. It's a very good way of making sure the part is correct. Or it sort of tells you a little bit on an envelope because you're guiding the DTI across the surface at one setting. The next one is Angularity. So that's basically two lines or two planes apart, 0.8 apart, and it's relative to a datum. So it's doing the angle of something, but it's also just two planes apart at a set angle. So again, one thing to comment here is, depending on the actual part geometry, some of these things are very difficult and some are a bit easier. So if you've got a very long angle, and the distance apart is 0.8 of two planes, because the planes are a lot longer, say on a big component, the actual angle variation is quite small. If your component's very small or the angle's very small, then 0.8 distance apart might actually give you quite a big angle allowance. So depending on the size of the part, sometimes depends on how difficult it is to manufacture. Okay, so we've got concentricity. So in this case, you want to make sure one diameter is concentric to another diameter, and the tolerance zone here is a diameter of 0,1. The center line of one of the diameters has to fall within that diameter of 0,1 relative to another diameter, for example. We've got profile of a line, which is a form tolerance here because it's got no datums. So it's the shape of something relative to itself. But because it's profile of a line, it's not got the line at the bottom of the symbol. It's basically doing a 2D. It's a 2D symbol, so it's taken at one section. Next one, we've got squareness or perpendicularity, depending on what standard you look at. So in this case, the squareness tolerance zone is a diameter of 0,1 or a cylinder of 0,1. So this would be on a round diameter. You'd be controlling the squareness in all directions. So you could do the squareness of a face to a face, so that wouldn't have a diameter symbol, or the squareness of a face relative to a cylinder, so that would have the diameter symbol on if the squareness tolerance is on the cylinder. Then we've got profile of a line, but in this case it's relative to A and B, so it's sort of positioning that surface relative to A and B. And again, profile of a line, 0.25, it's basically the actual profile of something in its exact position, and the total band between the two lines is 0.25 or whatever's in the box. Then we've got the most common one, positional tolerance, which you'll see all the time. And this is usually used a lot of the time on holes. You're positioning holes on a PCD or holes relative to other holes. So here it's quite important that we pick the A and B. A is usually the face that you're drilling into because you want the holes square to that face that you're drilling into. And then B might be a diameter, for example, that you're going to clock up. So to make sure that the machine is positioned in the middle of a diameter of something. Next one, cylindricity. So that's a 3D. Positional tolerance is usually a 3D. It's usually doing a hole, but on positional tolerance, you're measuring the hole at the top of the hole and the bottom of the hole, and you're making sure it's square to, say, the top face, which is A, for example, as well. So it's doing the squareness and the position. Cylindricity is the same as roundness, but over the 3D shape. So roundness is doing at one section, cylindricity is doing the roundness, but over the length of the part. So it's actually doing the straightness of that bar as well. So basically, it's two lines apart, 0.15, but over the length of the part. Next one is parallelism. So you might want one face parallel to another face. So normally you'd have datum A face, which might have a flatness on it, and then you want the opposite face flat to that datum A face. So we've got parallelism, and parallelism is two planes apart of 0.2. So parallelism controls the flatness of that side as well. So you wouldn't need to put a flatness of 0.2 on that same side because parallelism is doing that for you. If you wanted that side to be a lot flatter than 0.2, then you can add that symbol as well. But you don't need to add it as a general rule because the parallelism controls the flatness within that dimension that you're putting in there. Then we've got run out. So run out is slightly different to total run out. So run out is basically putting the DTI on the shaft at one location and measuring the run out. So it's in effect a band going all the way around the part, and the band between one line and the next line is 0.35, whether that's on the face or it's on a diameter. It doesn't really matter, you can do both. But the important thing is the tolerance band between the two lines is 0.35. So basically, you've got a shaft and you want to make sure it's running true. You put your DTI on the outside of the shaft and you measure it, see if the DTI is running within the 0.35. But then you take the DTI off and you move it along the shaft and you put it back on the shaft and you measure it in different locations. So that's run out. Total run out is when you put the DTI on the shaft and you guide the shaft along, you guide the DTI along the shaft at the same setting, so it's slightly different. So a single run out is not doing as much for you as a total run out. Okay, so we've got flatness. We mentioned flatness already. Again, it's another form tolerance. It's measuring the face relative to itself, which is why it's a form tolerance. We've got symmetry. In certain standards, they got rid of symmetry at certain times. And I think nowadays it's back in the ASME standard, it's back in the British standard, so it's still there. So it's basically saying you want something in the middle of something else. Then we've got profile tolerance for a surface. So again, I've just highlighted that as a form because it's got no datums in there. It's relative to itself. And then we've got straightness. So straightness, you can have the straightness of various things. If it's a cylinder, you'd have a diameter symbol, so it would be diameter 0.15. If it's a surface, it's just not got a diameter symbol in it. Okay guys, that's pretty much what I wanted to go through on this first video. Thank you very much for watching. Don't forget to watch the next ones that come out.